for the tested ultra-high strength steel, and these some conclusions. Next one. Okay. Next one. That's just to show the increased use of the ultra-high strength steels. Although we can use aluminum, even titanium, but because of the very good performance, such as high strength, strong toughness, and good ductility, the ultra-high strength steels are increasingly being used in the automotive industry, like trip steels. I think there are many papers about the trip steels here in this conference. Engineering machinery, mine exploitation, even the military and the aerospace industry. Next one, please. Just showing applications, for example, in heavy lift cranes, structural steels exceeding 1,000 megapascal in stress. Next one. And also, one more. In excavator buckets and bulldozer bladers, which is the focus of the present work, especially for this particular. Next one. Well, very brief overview of the master curve methodology. So this is the methodology is now codified in the ASTM E1921. Essentially, it measures the reference temperature for a given material, in this case structural steel, which is an arbitrary value. It corresponds to the temperature corresponding to a KJC of 100 megapascal per square meter for a 1T specimen. 1T is ASTM terminology, is 1 inch or 25.4 to be more precise millimeter of thickness. Okay, so it's standard procedure and it's standard specimen. So the idea is that that's the name master curve. All steels, at least for those covered by the standard, will follow this curve. The kind of description of the temperature dependence of the fracture toughness. Don't worry. Okay. A key assumption of the master curve is that the toughness, JC, which are converted to KJC, they follow a three-parameter Weibull distribution. Then we can see here that's the JC, is the minimum toughness or the threshold, the Weibull modulus, and the minimum, and the J naught is also called the character's toughness, which is close to the average toughness. It's not, but it's close. It corresponds to a failure probability of 63.2%. In some cases, but not the master curve, we can just use the simple two-parameter Weibull distribution. So there is actually no difference between these two distributions, just a matter of fitting. Next one, please. Okay, so the idea then is the master curve was actually made for 1T specimens, but then we are increasingly used sub-size specimens, especially in the nuclear industry. We had a paper this morning about this. And one idea or one primary objective of using sub-size specimens is to facilitate the testing. The loading is smaller, the material is equals to less material. The problem is that we then have to establish a correlation between the sub-size specimen and the 1T specimen. Oh, great. Thank you very much. Okay. How much? This is the single temperature method. So essentially, you test a certain number of specimens in a given temperature. The standard will cover all these aspects. And from these, running the procedure, then you establish the T naught corresponding to the median toughness of 100 megapascal square millimeter. And these will establish the dependence for the entire ductile tubular transition region, the dependence of toughness and temperature. A warning here, because my students make this mistake all the time. K is not stress intensity factor. For some reason, the master curve only works if you convert J to the unities of K, megapascal square millimeter, but it's not K. Okay, I think it's unfortunate these notation here. Call these other, give these other letter, but this is not stress intensity factor. Just J converts to unities of stress intensity factor. Okay, and another a more refined, let's say, procedure for the master curve is the multi-temperature method. So you actually test the specimens at several different temperatures, and from then, by applying a more sophisticated procedure using an iteration of this equation, you determine your T0. Okay, we don't have time. There are reasons for conducting a multi-temperature method, especially in surveillance and programs, but that's one of the, let's say, more precise way of assessing your T0. Okay, so these are the basic features then. It's based on high constraint specimens, so actually we cannot use shallow crack specimens. The specimen has to be A over W larger than 0.5, 0.6. And usually CP, compact specimens, or 3-point band specimens, high constraint. You convert your J to KJC, again, just to get the right unities. The toughness distribution obeys a Weibull distribution in the ductile to brittle transition, and you apply a thickness correction when you often use specimens smaller than a 1T or 25 millimeter thickness. And most importantly, the master curve, ASTM 1921. I'm afraid there is no European standard for this. This is just ASTM. Is essentially applicable to ferritic steels. So all ferritic steels, we yield stress in the range 275, 800 to 25 megapascal. This is in the standard. Anything outside the standard actually violates the procedure. And this was maybe 20, 25 years ago, was meant to describe the temperature dependence of toughness, of fracture toughness, especially for pressure vessel steels. Okay, that was the main purpose of the standard, and now it's being applied to other materials as well. So the objective of this work is to evaluate the applicability of the methodology to describe the temperature dependence of toughness for a different material, in this case, an ultra high strength Martensitic steel. And that's the tested steel. It's a commercially named AR40450, which is very similar to Hardock's 450. Okay, so it's a wearing resistance steel, very. So you can see here, it's a very high strength. It is the stress strength curve at room temperature. So the yield stress is almost 100 and 1,000 and 250 megapascal. And you can see here the very low hardening behavior of these steels. So as soon as it yields, it goes up a little bit, and then it's almost flat. So it's almost essentially plastic material. Okay, you can see here then the microstructure, Martensitic, and the microalloy, the alloy. These are the Sharpie properties of the steel, and it's very important. Okay, usually we perform a hyperbolic tangent fitting of the Sharpie to get the temperatures corresponding to 27 joules and 41 joules, and these are very important estimates that will tell us at which temperature we should test our specimens. Okay, so when we then employ what's in the standard, so the standard will tell you, okay, you get your 27 joule temperature and subtract by minus 18, then you get the test temperature minus 21. If you use the 41 joules as your parameter, then you get a 66 recommended 66 temperature. Okay. These are the toughness distributions. I'm sorry, it's a little crowded here, but you can see for the lines, 1T specimen, SCB specimen at 50 degrees, then the 1T specimen at 60, the 1T specimen at 70, and we also tested the pre-cracked Sharpie specimen, which are the 10 by 10 40. Okay, so it's a Sharpie specimen, but tested on the brain. It's not like an impact load. You see here that the scatter, almost no scatter. Okay, so and nevertheless we still fit the distribution, a Weibull distribution. Just follow the standard. So the question remains: okay, what's the what would happen if instead of using the maximum likelihood estimate of the Weibull parameters, using the standard, which has a fixed value of 4, okay? There are reasons for fixing this value as 4. We don't have time here to discuss. We can discuss this later. Or if I just perform a standard maximum likelihood estimate, you can see here, okay? The huge difference in the scatter. By the way, I didn't mention this. The Weibull modulus, the alpha parameter, measures the scattering data. Okay. So as you can see here, the data is not very scattered, and this will be reflected in the actual Weibull parameters. Okay. However, what's very good here is that the K0 does not vary very much. Okay. You can see here K0 varies from 112 to 115, 141 to 144, and so on. And K0 is the key parameter to determine T0. That's what it is very important, this assessment. Okay? The load displacement curves. So these are the load displacement curves at minus 20, 20 degrees, 50 degrees, and 70 degrees. So that means that if we were using the estimate given by the 27 joules expression, which actually is the one recommended in the standard. Because remember, the standard was made for ferritic steels. We would be way off the right temperature, because at minus 20, you can see here this is load and CMOD, crack mouth opening displacement, is almost linear. So at minus 20, sorry, at 20 degrees, okay, just put your specimen on the machine and just test it. It's a room temperature. It's linear elastic fracture mechanics. Okay? So we start to get some plasticity at 50 and at 70. So that's why, and this corresponds better to the estimate of the 41 joules. Okay? So this is also was also a nice outcome, because this will suggest us what? Okay. Okay. So this is the 1T then at 50 degrees, okay, 45, 47. Very interesting is that's very interesting. We saw no plasticity in the crack front, but we start to get some quasi cleavage pattern here. You can see here some cleavage facets and also some dimples. At 60, okay, 41. At 70, 45, but surprisingly, at 45, at 70, we got a lot of, even though we didn't have any plasticity in the crack front, we got a lot of dimple structures, which is strongly connected to microvoid coalescence and growth, typical of ductile failure. Okay? And the pre-cracked Sharpie, I'll go very quickly, and this is the multi temperature. Okay? This is the summary here. So we got very nice estimates for several temperatures, including the multi-temperature. So I'll say that the T0 for this material is 44 plus minus 3 degrees. That's probably very good. Do I have time to conclude? Okay. You have to give me some time because of the reservoir. Okay. Okay. So while the tested steel, it's Martensitic steel, does not fall into the procedure of the requirement of the ASTM standard, the procedure still appears to provide a very good description of toughness with temperature. And one of the reasons for this, okay, let's discuss this later, is that actually it's not very important if you satisfy cleavage fracture, because that's what the standard tells you. You need to satisfy cleavage fracture. But you saw a lot of dimple structure. So it looks like it's much more important to satisfy the statistical distribution, the Weibull fitting, than the actual microstructural, micromechanics of the microstructural failure. Okay? Of course, this is a limited experimental data set. Okay? So actually we are hoping, actually we have a next ASTM meeting in November in St. Louis. Everybody's welcome to attend. So we're hoping to extend the procedure to other classes of high strength steels. Okay? And of course we need more data to validate this. That's all. I think it's, okay. Thank you very much.